So this is the third question for the mechanics step 3 support booklet. We've got a circular hoop with a mouse running inside it, so we know it must look a bit like this, I guess. The hoop is suspended from P, so there must be some kind of tension force holding it up. Not that this will matter in any way. The hoop has a mass, I guess, of, let's just call it big M with an mg coming down like this, and then we've got a, I'll say little m mg coming down like this for the mouse. Um, yeah, of course, we need some angles here, so let's construct some angles. We'll call this angle here theta. Um, and now we can also, therefore, I mean, we can resolve some forces, right? There's a normal force from where the mouse makes contact with the wheel of big N, and there's also a frictional force. Now, frictional force goes in that direction. It's very tempting to say that the friction will go this direction because the mouse is trying to run this way. But like, imagine that this wheel was made of ice. This mouse would have no hope at all of getting up this wheel, right? We've all tried to climb a hill that's very icy. The friction has got to be working with you to make sure you climb that. And also, like, the only actual force that's acting on this mouse is this mg, which will eventually be, there'll be a component of which coming down this way. So that friction's got to balance with that. Otherwise, the mouse will just literally just fall down. So friction's got to be acting up the slope like this in this case. And then we finally need one more angle, which is the angle up to here to the mouse. And the reason we need this is because we're about to take moments from P. So we need to know the distance and the angle from P to the mouse. Now this angle here will be theta over 2 because of circle theorems, saying the angle at the center is double the angle at the circumference. Now this is awkward to use, so we'll just call this one 2 theta and this one theta, and then we'll make some more progress. Now, if it doesn't rotate at P, if the wheel is not rotating either way, then that means that moments, well, P is in equilibrium, but moments are in balance at P. So we can take moments at P. Mg and little mg are both acting straight downwards, and T is acting straight upwards. So they're completely irrelevant to the moment, the turning force at P, because all of them have zero component directly left or right. So we can ignore all those, and we can just look at these two forces and the distance from them away from P. We can call that distance PM, I guess, where M is like the position of the mouse. Apologies for confusing that with this M or this M, but yeah, whatever. So distance we'll just call PM, this distance. Now we need to resolve some forces so they work parallel and perpendicular to that thing. So we'll do some angle chasing. Because of the isosceles triangle here, this is theta. And because of the 90 here, this is 90 minus theta, which means if we were to resolve FR this way, because that's another 90, we could say this is theta, which means this is FR cos theta going in this direction. And now we have the turning going anti-clockwise is PN, the distance PM to the mouse, times FR cos theta. And now N, we can resolve this way. Again, if this is 90 here, we could call this 90 minus theta, which means this is N cos of 90 minus theta, but cos of 90 minus theta is the same as sine of theta. You could also just place N up here maybe, and say going across is opposite theta, so that's going to be sine, but it's up to you how you do that. But anyway, we can resolve forces like this. The distance from P to the mouse times this force must be equal to the distance from P to the mouse times this force. Now, of course, the distances cancel, and we can rearrange that just a little bit and maybe end up with something that looks a bit like this, I guess, and I'll pop that at the top up there. Because now it says we're being asked to show that we can choose its speed such that we remain everything essentially remains in equilibrium. So now we need to focus on the mouse a little bit more and resolve some forces there. So coming down here, if we just draw a line like this, of course, this is going to have to be 2 theta as well, because I don't think I ended up using this line. Okay, just ignore this line coming up. This is 2 theta, which means this, of course, is mg cos 2 theta. And of course, this down here would be mg sine 2 theta opposite the angle. And then we can also resolve, or in fact, FR is already resolved, right? Because it's already going perpendicular to the point of contact. So now we can set up motion for the mouse in terms of parallel to kind of the way the mouse is moving and perpendicular to it. So what we can set up is, firstly, if it's got its speed of u, which we know it is, then that means the acceleration towards the center is u squared over a. That's just a piece of theory that we should know. And also, of course, if its speed is constant here, then that means that there's no acceleration horizontally speaking. Otherwise, it would be slowing down or speeding up or moving up or moving down the plane. So we know that FR must balance with mg sine 2 theta, or one minus the other is 0. So this is just F equals ma, where the acceleration is 0 going up and down, and then this is F equals ma, where we're going in and out towards the center. So n minus this one is equal to, because the acceleration acts inwards like this. towards the center, times by m. So that's just f equals ma. Okay, so now we have three equations, and we need to come up with some kind of equation for just u. It wants us to talk about u here. So let's just try and isolate u from all of this business. There's a few ways you could go about doing that. I decided to write fr is n tan theta and then replace it in this equation and move the other thing to the other side. And then you can also, I guess, replace that in here as well. So here, this is just this equation rearranged for n. And then I think I did this one divided by this one to just get tan theta equals this over this. Yeah. And then we can cross multiply. We can also write the tan theta as sine over cos. And cross multiply, we can also cancel all the m's, which is very helpful from this fraction here, because they all have m in them. Cross multiply, but also notice that the signs cancel. This cos will make a cos squared up there. I still haven't cross multiplied yet, I just did that. But now this is really nice, right? G cos squared minus G sine squared. Take away G cos squared on both sides and add G sine squared gives you over here G cos squared plus G sine squared. And of course, factorize out the G. Cos squared plus sine squared is 1. And then times the A over here, and we end up with U squared equals AG, which is nice. So that's our that's the constant speed that the mouse needs to choose if a mouse is, capable of making choices like that. U squared equals AG is what we need to do. Describe what happens to the hoop when the mouse passes the point at which AOM is 2 arctan U. So okay, what on earth does that mean? Well, eventually, if we get high enough on this hoop, there will be a point where friction can't output enough to hold us in place. So let's think about the limiting equilibrium of this system here. So, of course, we have this here. All I've done here is I've replaced u squared with ag, and there's some cancelling, and you get down to here. And, of course, fr I've just can write as well. But again, there'll be a point where max fr is when we have n, is n times ug, I guess. Also, sorry, before I get to that, I'm going to take these two equations with the replacement of u, and I'm going to rewrite the cos 2 theta, because, it's very natural to factorize out the mg here. But then I only spotted this because I've done a lot of integration of things that look a bit like this. You can replace that using this idea here with 2 cos squared. So we can write it like this instead. This is much more obvious to replace. Of course, it's just 2mg sine theta cos theta, which I will do eventually as well. But of course, max FR, the maximum friction can output, is n times mu, right? It's the normal reaction times mu. So okay, well, we can just times this, which is this I'm using now, times mu, and set that equal to our FR. And we can find for what theta we have that maximal output. Well, okay, like I said, sine 2 theta can be written as 2 sine theta cos theta, and now cancel some cos thetas and divide by cos theta and cancel a lot of 2mg stuff, and we end up very quickly with u equals tan theta. So therefore theta is arc tan u, which is half of what they wanted me to get. But then you can remember, of course, that, well, that means the angle, they're describing the angle AOM, which is this angle here, which is twice theta. So I just need to double this and say at 2 arc tan u, we are at the point of limiting equilibrium. So if we pass that point, friction is not going to be able to hold the mouse in place, and the mouse will start slipping down the slope. Now, even more specifically, what happens to the hoop itself if the mouse starts slipping down? Well, of course, it's going to rotate. Which way is it going to rotate? We can head all the way back to our moments equation to find out, I guess. I think probably the easiest way to see it. If we go all the way back to our moments equation here, if the mouse slips down the slope, that means theta will be getting smaller, which means cos theta will be larger, sine theta will be smaller. So this force will be the larger one. And so the hoop will rotate this way around, because this is the force that's pulling it this way. So I think the hoop will rotate. Well, it depends which side you've drawn the mouse on, but I think you can get away with just saying something like the hoop rotates the other way to where to the direction the mouse slips, because you could have drawn the mouse on this side, I guess. Something like that I think would be fine. The next question then is actually very similar. We've got a mass inside of a hoop, kind of the same situation. We've got a 2 phi here and a phi here, because as we saw last time, that was an easier setup to use. The only real difference here is that we've got a string from the top of the hoop connected to this mass. And initially the thing is in the middle, and the string is stretched pretty far, but it's kind of in balance because the thing's right in the middle. And then the mass is pushed slightly to the side, which makes then the string able to sort of pull it up the hill, if you like, until we reach a point. It says it comes to rest when the string becomes slack. So it comes to rest somewhere over here. where this string is now slack. Now it's talking about finding the modulus of elasticity. Now it's tempting to see if you could do some kind of force equation with the mass right at the bottom, with like the extension here, the tension coming up, and then the mg down. But then you'd have a reaction force that you don't actually know. So you can't really do that. You need to consider energy instead, I think. So when we're all the way up here, of course, we can think about the gain in potential energy. There's a little equilateral triangle here, right? Because radius A, and therefore this is A as well. And then we've got angle 60 everywhere. So of course, this height here is just a half A. Um, and so if this is A as well, then this whole total height is 3 over 2A. So the gain in potential energy is just m times g times 3 over 2A. And then we have the loss in elastic energy. It used to be stretched because the natural length of the string is A, and it used to be length 2A. The stretch therefore was A. So elastic energy is given by this formula here. So that would be lambda A squared over 2A. Bit of cancelling there. And then these two things must be equal because the thing is at rest at the start, and it's also at rest up here. So these two things must be the same. And then we could just do some stuff, and we get lambda as this pretty quickly. Then it says, it's actually now asking us to speak about the reaction force, which they've called R. So, okay, we need to do a couple of things here. We do need an equation to do with these forces, but we also are going to need an equation to do with the energy as well. Otherwise, we just don't have enough information to, like, essentially we put them together a bit like a simultaneous equation. So let's do the energy first. It obviously doesn't matter which one you do. But if we just say that this mass is on a random point on the sphere, on the hoop, sorry, with angle phi up here, then we can say, well, okay, we've got obviously a cos 2 phi here and a cos 2 a sine 2 phi here, just by doing basic trig stuff. And that's useful because we can then talk about what length this string is at, because one of the energies we need is elastic energy. So let's talk about the length of this string when it's at a random point with phi being the angle. Well, we can do some Pythagoras here, right? Because this length is a plus a cos 2 phi. And then, yeah, we can do some Pythagoras. We can expand this out. Possibly easier to just factorize out the a and then use a double angle formula here, but I think eventually I get that done anyway, because this is just a squared sine squared, and then of course you can factorize out an a squared here. Cos squared plus sine squared is 1, so that's just a squared plus a squared is 2a squared, and then I factorized out the 2a squared, and this is where the double angle formula can come in now. You can write it like this, right, and you can replace it in. If you add the 1 to both sides, then you can just see that this is 2 cos squared. Which roots really, really nicely to this. Of course, length has to be positive. So it roots really nicely to this, and that will be our L. And therefore, our extension is not that, right? Our extension is that minus A, minus its natural length. So our extension is this, which we'll use in our energy equations in a second. We also need to think about the potential energy. So the gain in height, well, again, this is still A cos 2 phi. So therefore, this little height, which is the gain in height vertically, is just A minus this. So that would be A minus that. And our velocity, as we saw in the last question that we did in this video, is just, our velocity is just R, or the radius of the circle, times the angle of velocity omega, which is the same thing as theta dot, right, by definition. So this is just this 2 theta dot, because that's the angle made with the center, apologies. So it's A times 2 theta dot. That's just R omega, essentially, but omega is this. Maybe the dot should go there. It doesn't make a difference, obviously, because 2 is just a constant, so it's not going to matter. Okay, so we have, and now I'm going to build the energy equation, right? Initially, the only energy we have is the stretch in the elastic strip. When the thing was like at the bottom here, we just had a stretch of A in the string, and it wasn't moving, and it had no potential energy, so it's just this. When it's here, we've got a little bit of a gain in potential energy, which will be m times g times this height. We've got a gain in the velocity, or kinetic energy, I should say, which is a half times v times m times the v squared. So that's our gain in kinetic energy, and then we have the elastic energy that still exists in the string when it's here, which is again using the lambda times a squared over 2l formula, is going to be this thing here, where we know lambda now, so that's really helpful. We've put it in both of those as well. So we've got a long equation here. So we're going to just write it out, and then we're going to simplify a lot. I made so many mistakes when simplifying this because I was trying to do it too quickly. But, there's a lot of m's that cancel. I think I doubled everything just to get rid of these 2's at the bottom. Some a's cancel over here. I think I've already pulled out an a squared because there's an a in each of these brackets. You can pull it out as well and then cancel it with this. So there's a lot that can be done here. Then of course, you've got some expansion of double brackets here. And you've also got changing this into the same double angle formula we saw just a second ago. Everything starts to group together. We have this annoying term that there isn't much we can do with, but this is where I was mentioning, this is just half of our work here. This is just the bit that gives us half of what we need, and then we're going to consider the forces to get us the other half, and that's what's going to get rid of this term that we don't want. So I'm going to park this here for now. That's just for a few more things simplified. Going to park it there, and now we're going to think about forces when it comes to this diagram here. So what we can do is, of course, force in a string is lambda x over L, so we're going to need that formula at some point. So this tension here is just going to be lambda is 3mg, as we've already seen before, and then the extension is that same extension we had earlier, and then L is the natural length of A. Of course, the A's can cancel, and you can expand out, and you get this. So now let's resolve the forces towards the center. So coming down here, we can call, this angle is obviously going to be 2 theta, because it's corresponding to this, sorry, 2 phi, because it's corresponding to this 2 phi, which means this is mg cos 2 phi, and then this is mg sine 2 phi, but I'm not going to need it because I'm not interested in forces parallel like this. I'm just interested towards the center. So I can also say that because of this isosceles triangle, if this is phi, this is also phi, because you've got two radiuses here. So this force is not only r, the reaction force, but it's also t cos phi. And now we can set up F equals ma. We do have acceleration towards the center. The acceleration towards the center is given by the formula v squared over r. R is the radius, that's just a, obviously. And v is that same v we saw earlier of the one that I used before on the previous slide, where is it? It's this essentially 2a phi dot. It's that same force there. So we'll put that in as well. 2a phi dot or a2 phi dot or whatever. It's just r times omega, and omega is again 2 phi differentiated, which is 2 phi dot, I guess. You can square it out, and then this term is great, right? Because this is the same term we saw when we did the energy stuff. So I'm going to be able to substitute this out, and I'm going to be able to create an expression in r that just has all the things that I want it to have in it. Now the rest of this line, I should say, is just r plus this here is t cos phi, right? Because that's t from this expression. And then this is the opposite force, which is mg 2 phi, cos 2 phi, going the other way. So we get this expression here. Of course, there's an m here because this is F equals m times a. And that's just the a there. So that's the a's have cancelled a little bit as well there. So okay, we've got some work to do here. That should have come up earlier, but whatever. We've got some work, just some expanding to do. Again, replacing this double angle with a square instead, because then things can start to go together. And we'll end up here. And now we can just set this thing here equal to this thing here, except up here I need to times everything here by m, because of this m here. So I'll just times everything with this by this in here by m, and then set it equal to this thing over here. And then we can do some tidying. And we end up with exactly what we needed to get, except for the fact that there should be a -1 times factor here somewhere. Like every sign is just wrong, right? So I looked through my working quite carefully here to see why I somehow got this wrong. Before finally reading that this is talking about the magnitude of r. So maybe this isn't even a problem, because the magnitude would just be the positive version of it. And the positive version of it is just this. As long as that's only really true as long as this thing is always negative, because then the magnitude would just always be the positive version of it all the time, right, I guess. So let's just quickly go ahead and show that this indeed here is always negative. And we can do that in a couple of ways, but probably the most mathematically pleasing is to complete the square. You could just write this as some kind of pseudo-quadratic and then show that it had no roots by finding the determinant, not the determinant, the discriminant. I always get confused with those two words. But completing the square is probably quite a neat way of doing it. I factorize out the minus because I hate completing the square with minuses in them. And then, of course, factorize out 12, halve this number. You don't really have to do 24 times 24 here if you don't want to, because you're going to have to times it by 12 at some point anyway. But again, if you do that, you get this. 5 times 48 is like 240, if I can do mental maths, which makes this slightly bigger than this. So we get a plus, I think, 15 over 48 left over. And now this thing here is always positive, right? And I've got a negative on the outside. So this R is indeed always negative for all values of phi. So therefore, the magnitude is just the swapped version of this thing. And also, it should be mentioned, because it says so here, this is always non-zero as well, because this term is always making it slightly negative. So therefore, the magnitude is just the swapped version of it. And of course, it's also never zero either, because the other thing wasn't either. And that's that question done. Thanks for watching.